All right, hello, mother lovers. Another TMUA for you. Paper 2 from 2016 today. Let's get going. First one then, got some integral to do. So let's just expand those brackets out. What we're going to get, x to the 4 for the first bit. Times in the x squared, and the 1 over x squared together gets rid of it, doesn't it? So we'll have that minus 4, but there will be 2 of them, so it's like a minus 8. And then squaring the bit on the end, we'll have a 16, x to the minus 4. So we want to integrate that thing and plug in the value of 1 and 2. The x to the 4, we'll get a fifth of x to the 5. For the 8, we'll get minus 8x. And for the 16, we'll raise that power to minus 3 and then divide by the minus 3. So minus 16 on 3. We go and plug in the value of 2 and the value of 1. You could think about making a common denominator now. It's probably easier to plug the numbers in first, and then you'll have like easier bits to do it with and then deal with it. So doing that, what do we get? We'll have 32 on 5 minus 16 minus, it's going to be an eighth. So 16 over 8 is 2. So minus 2 on 3. And then for the 1, nice and simple, we're just going to have 1/5. We're going to have minus 8. And we're going to have minus 16 on 3. Remember, those second ones are all going to be taken away. So what do we get? We get 31 on 5. We get a, let's be careful with our negatives here on the 16. So minus 16 plus 8 is going to be minus 8. And then we're going to have, again, similar sort of idea. It's going to be plus 16. So minus 2 plus 16 is 14. So if we think about, sorry, that should be plus on that one. So just double check. 2 pluses make that big. Obviously 16 is more than 2, so we should have a positive thing. Now then we'll make this over 15. So the first one, times it by 3, we'll have 93. Second one, times 15, we'll have 120. And the last one, times 5 plus 70. That's minus 50. 93 minus 50 is 43. All looks good. Double check. Yep, here's the answer. Similar sort of one here then. We want to differentiate this thing, don't we? Look at, yeah, what's f dash of x? So if we think about what's the power on the bottom, might be worth looking at by itself for a sec. So it's x cubed, but over 4. Expanding the top, what do we get? 2x cubed plus 10x. So doing that division, 3 take 3/4, we'll be left with 9/4. And 1 take 1/4, we're left with 1/4. To differentiate in, we'll have 9 over 2, x to the 5 over 2, plus 5 over 2, x to the minus 3 on 4, which is, yeah, b. Oh, looks good to me. You could have done that as well just with like either numbers, like just the coefficients. You see they're all different, like everywhere. Or just with the powers as well. That would be fine too. So what is the value in radians of the largest angle between 0 and 2 pi that satisfies this equation? Well, we've got sine squared and cos squared. So let's take, we've got the smallest number is 4. So let's steal 4 from the biggest one and make the 4 with those bits. So i.e. we're going to have, like, instead of the 8 sine squared, 4 sine squared plus 4 sine squared plus 4 cos squared equals 7. These bits are just 4. So 4 sine squared is 3. So sine is going to be plus or minus root 3 on 2. Drawing out the sine graph quickly, where we get that value, I think it's going to come across at the top and the bottom for the plus or minus root 3 on 2. 1, 2, 3, 4 answers. We want the biggest one, so we do want to be on this one at the end. If you think what the answer gets, if you do the normal one, just inverse of this on the calculator, what you get is 60 degrees, isn't it? So it's pi on 3. So we're pi on 3 from the end, pi on 3 from this far end as well, so it should be 5 pi on 3. D for number 3, is that correct? Yeah, D. Lovely jubbly. Now we've got 5 urns, P to T. They've each got the same number of balls in them. So we've got all these urns, all the same number of balls. One of them telling the truth, 4 of them are lying. Which one is which? Easiest way here, like, it's hard to tell, like, is this true and false, like what ones are going to be allowed. We know they have the same number of balls. So we could just say, okay, do they all have 1 ball in them? If they have 1 ball in them, who's telling the truth and who's lying? If we look at like P, Q, R, S, and T. So if it's 1 ball, P contains 1 or 4, so P is being truthful. Q has 2 or 4, so Q is lying. R contains more than 2 and fewer than 5, so R is lying. R contains 1 or 2, so S is telling the truth. But only one of them is true. So that tells us that we can't have one ball in there, not allowed. Let's look at 2 then. 1 or 4 for P, so they're lying. 2 or 4 for Q, so they're telling the truth. More than 2, and fewer than 5, more than 2. 2 is not more than 2, so they're telling a lie. 1 or 2, so they're telling the truth. And again, we've got 2 truthers. We can't have 2 truthers, only 1. So that's not true. Let's just keep going to number 3. For P then, 1 or 4, that's not true. 2 or 4, that's not true either. More than 2, fewer than 5, that is true. 1 or 2, that's not true. Fewer than 3, 3 is not less than 3, is it? So that's not true either. So if there was 3 balls in there, 4 are lying, 1's telling the truth, that must be the answer. Who's telling the truth? It's going to be R. Is that correct for 4? Yep, all good to me. Number 5 then. Consider the statement, a whole number n is prime if it is 1 less or 5 less than a multiple of 6. How many counterexamples are there in the range 0 to 50? So it's not, that's like the kind of reverse thing. It's like, if you're this, you're not a prime, but if you're a prime, you are this, basically, unless you're like 2 or 3, I think is the only ones that rule out from that rule. Everything else, though, is going to be 1 or less, 1 more or 1 less than a multiple of 6. So let's just go through, write them all out. What can we get? Well, think about 6, we'll have 5 and 7. And then for the 12, we'll have 11 and 13. And we just continue this pattern all the way down. It's going to be easier to do the top altogether. 35, 41. Let me move over a bit and give myself a 47. And then these are going to be 2 more than all of those. And also remember, 0 is a multiple of 6. So we will also have 1 down that end. So if it's a counterexample, we need to make sure that it's not prime. So which ones of these are not prime? 25, 35, 49, and I think there's one more. Where is it? Am I being silly? 5. Oh, 1. Yeah, 1. 1's not a prime number, is it? It's a unit. So the answer should be 4. Lovely jubbly. Next one then, some sequence. We've got some sequences, sequence functions. The first one is x to the power 10, and the next one is made by differentiating the first one times it by x. So let's have a look at what is f dash of 2. Well, f dash of 2, just f of 2. That's going to be equal to x times the derivative of f dash of 1. So that derivative would be 10 x to the 9. So we end up with 10x to the 10. Similar thing if we look at f3. What's that going to give us? X times the derivative of this thing. So bring that 10 down, we'll have 10 squared, x to the power of 9, and then we'll times those x's together again, 10 squared, x to the 9. And we can, sorry, x to the 10, x to the 10. And we can see some pattern building up here. Every time that we do this, like the differentiation loses a power of x, but then times it by the x brings it back. So the power of x should always stay the same. It's always going to be 10. And the differentiation introduces a new factor of 10. As you do the differentiation, this 10 comes down, doesn't it? So think about where it was. Over here, it's going to come down times together to make 10 squared. So every next function is going to be 10 times bigger than the last one. That's it. So what we have, f of n is going to be equal to 10 to the power of n minus 1. The first one didn't have a 10, did it? The second one had 1 10. Third one had 2 10s. And then we'll times that by x to the power of 10. That looks good. We now want to find the value of the sum of the first 20. So x to the 10 can come out. I'm not going to be cycling through that at all. It's just a factor of everything in it. So it will be some multiple of x to the 10 we have at the end. And you can see that they all have x to the 10 in them somewhere, don't they? So that's good. So what do we need to have? This is the same as x to the 10 times by the sum from n is 1 up to 10. So to 20 of 10 to the n minus 1. Let's think of what is this then. Well, we're going to have the first term will be 1, sorry, then 10, then 100, then 1,000, etc. We're just timesing by 10, adding that on. So the first term is 1. The common ratio is 10. So the sum of the first 20 should be a 1, r to the power of n, which is 20, minus 1, over r minus 1. So looking at that, what does that give us? Well, top doesn't really do much, does it? 10 to the 20 minus 1, all over 9. And we still need to times that by the x to the power 10, yeah? So really, we want the actual answer is x to the power 10 times that thing. X to the 10, x to the 10. So do we have a 10 to the 20 minus 1 over 9? Let's look at the over 9s. I've got 2 of them. One of them, 10 to the 20 minus 1. So C for question number 6 is correct. Lovely. Looks good. Let's keep going. Oh yeah, some proof, this proof thing. We've got 4 numbers, A, B, C, and D. They're all real, and they're all bigger than 1. They satisfy this equation. So log base C of D is equal to log base A of B all squared. We want to basically prove that this is going to be true. And they've given us some lines. We have to pick and choose which ones we need to do. I'd kind of recommend just not look at these for a second and just try and prove it yourself. Like, you want to end up something similar like this. The only one you really need is like the first definition of what is x and y to do. So let's use those and just replace bits that we can replace. Log AB is x. So this straight away tells us log base C of D is equal to x squared. And you can see what we wanted to do is, like, we don't want to have this C on there. So we can raise both sides to the power C. We're going to have that D is equal to C to the power of x squared. This looks good. We want to take log base B at some point, don't we? But I'm not thinking we're going to do that now, because we do need to kind of follow this path, don't we? So we have D. That's good. You can see the D stays there for the next section. So what do we need to do somehow to really get rid of C? Yeah. What is C? Well, we have over here a relationship with C. So we can say that C is equal to A to the power of y. So doing that, the D becomes A to the power of y, all to the power of x squared. When you have this situation, you've got like something in there, all to the power of x squared. That's exactly the same as times in those powers together, x squared y. That looks good. You can see we have then, like, what lines have we got so far actually? D was equal to C x squared. So we've had C, obviously we've used 1 as we have to use 1. And then we've got something like this. Which one of these works? This one works. Which looks good. And now we want to keep going next. But now we can kind of go down here and see, like, what options have we used? 1, 3, 5. So we needed to be 1, that's good. Had to be 3, and then had to be 5. So it must be that one. If you do follow through, it works out the same as well. So what's going to happen next? We need to go through and think 1, 3, 5. We're then going to have 9. Is that true? Yeah, that's the line I've had, yeah. And then we want 7. Is that true? Yeah, I can just, in the same way that I was able to combine these together, I can split them up in any way as long as they multiply together to make x squared y. So I can take one of those x's away and leave an xy out there. And then we wanted 4. So D is equal to B to the power of xy. Well, we do know from this that B will equal to A to the x. So that's going to be true as well. And then we want to do star. Okay, so from that point onwards, we're just taking, I'm sorry, this one. Log base B is both sides. You'll end up with log base B of D is equal to x times y. And we can see that these bits, that's x, that's y. So that looks good to me. C is the correct answer. Number 8 then. The region is defined by these inequalities. Consider the 3 statements, blah, 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 which the following is or are true for every point in the region. Okay, well, let's draw these out first. We'll get some x-axis, well, some y-axis first, then some x-axis. This one's nice and straightforward. We just want a line that's going to come through at 6 on both of these. So completely like negative diagonal line. This is being 6, and this being 6 too. This one, bit of rearrangement. Add the y to the right-hand side. So it'll be y less than, add that 4 over x plus 4. So let's draw the line of x plus 4. Come through somewhere like this, won't it? Getting perfectly like positive diagonal gradient, just 1. We have that coming through at a value of 4. Where they intersect then? Well, they're 2 apart here. They all move by 1. All the gradients are 1 or minus 1. So this point here is 1, 5. Where they're intersecting there. So we can see for part 1, like any point that's in this region, because that's the region we want, we need to be bigger than 6. So we're not allowed to be on this side of it. And we had to be less than x plus 4. So not allowed to be on that side of it. So we have our kind of Goldilocks zone over here. This pulls the point 1. Everything is therefore at least 1. Nothing can be lower than 1. So that one is correct. Bigger than 5? Well, clearly not. So you're lying. This one's a bit harder to look at, yeah. You could trial and error to try and get some numbers in there. Think about what this means. It's probably easier to pick positive numbers in it and work with instead of trying to do stuff with negatives. So what we can do, if they're both positive, this one's positive. We need to make it be negative though, or at least not be negative. So actually no, we can make sure that it just fits in here and gives us an answer that is positive. So if we pick any numbers that as long as x is bigger than y, we should be fine. So let's have a look. What numbers can we pick? Well, I can pick 6, 5, yeah? So if I make x 6 and I make y equal to 5, what do we get? We get 6 plus 5 times by 6 minus 5. That's 11 times by 1, which is 11, which is bigger than minus 24. But is it true for every single point? Can we find one that breaks? So can we do the other way round and find something where actually y is bigger? Well, yeah, we can go, instead of thinking about this point, let's have you just move down. What if we do, like, not this exact point, but we can move one to the right? And think about basically having x equal to, let's do 10, and y is equal to 11. So all we've done, no, we'll do 12 even, sorry, 12. So when we look at this now, they add up again to a big number. But x is bigger than y now. So that's going to mean, sorry, y is bigger than x even. So we get something negative. So when we times them together, we'll get 22. Take them away, we get minus 2. Times them together, minus 44. And that is clearly less than minus 24. So this one is not true. So answer is 1 only, which should be B. Is that true? Yes, it is. Number 9 then. Two triangles have the same area. Which of these x conditions, taken independently, would imply that they are congruent? Okay, so same area, what does that tell us? Generally, we're going to have like A, B, sine C is the same in both. You could think about half, obviously, but the half's going to be in both. You can get rid of it. So it's going to be the same in both triangles. So we can always start with that. Here we have these points. Remembering that what this refers to is always having angle C between side A and side B. So in this case, we think about the two sides that we've made equal, AB and BC. The bit that joins those is B. So we're thinking about B and Y for a similar idea, like Y is in both of them. They're not very good letters. Let me try again. B, Y. That didn't go much better, did it? But let's keep going. So we know the areas are the same. So we can start from this being equal. We know that AB times BC times sine of B should equal to xy times by yz times by sine of y. We can cross some bits out then. AB is the same as xy. BC is the same as yz. So we do have that the two signs are the same. But if we want to make them congruent, we need to have the rules for congruence, like SAS or SSA or all sides. Yeah, all sides, SSS. You need 3 facts in it, SAS, ASA, and SSS. 3 facts, and at least one of them has to be a side. On this case, though, we have the signs being the same, not the angles. We have 2 sides, so we would need to have either another side or another angle. All we know is these signs are the same, not the sides. That doesn't tell us the angles are the same. Because we could have a situation where you have like 60 and 120. Do you know what I mean? So they both have the same area, but they're not the same triangle. So one does not give us congruence. If you have this situation, very similar scenario now, we have B and Y being the ones in the middle. So we can actually copy down, you can copy this thing and just cross out the bits we need again. So let's change how we cross these out. What ones are the same now? Well, X and Y, A, B and X, Y. And the angles are the same, so the signs are the same. So we have that BC is equal to YZ. So altogether, we're going to have one side, one angle, and another side. So 2 sides and an angle. So this one is completely fine. It's going to be from SAS. Down here, then we've got 2 angles. So that tells us the third angle. So all 3 angles. That tells us they are similar. And when you add in then the same area, you're going to get the fact that they are congruent. So you have your sim plus area equals congruent. That's not very good writing, but does the job. And we get the marks for that one. So it should be not 1, but yes for 2 and 3. So not 1, so it can't be down there. It needs to be one of those. Yes for 2, so it can't be up there. And yes for 3, so it can't be there. So it must be D for number 9. Number 9 is D. Lovely. Looks good. Let's see number 10 then. In this question, x and y are non-zero real numbers. Which of the following is sufficient to conclude that x is less than y? So we basically wanted to do some function to them to make sure that they stay the same, so that they stay in the same order effectively, or at least they're going to completely reverse order. You can go through and find some examples for all of these and figure out what's going on with them. The easiest way to think about it though is the fact that when we have x to the 4, this both increases and decreases. If we have 1 over x, again, it both increases and decreases. Whereas if we think about the 3/5, it doesn't. It is monotonic, I think. It always goes in one, it never changes direction. Do you mean? Is that what that means? I don't know if monotonic allows like stoppages. We can have a turning point, but we can actually turn. Monotonic, so a stationary point, I suppose. Monotonic maths meaning. Does it allow turning points? Either way, we don't want our function to ever have like, it's always increasing, always decreasing. It can be flat, but it never does both of them. Do you know what I mean? We want either or flat. And that's, you can see here, this is an always increasing, or it's a never decreasing function. Never decreasing. So that's the only options that we can have. And because it's always increasing, it's or never decreasing, do you know what I mean? It's going to preserve the relationship between them originally. So if x is less than y, when you do this function to them, it just kind of exaggerates that gap or shrinks that gap depending on where the numbers are. Bigger than 1, it will exaggerate the gap. No, shrink the gap. Smaller one, it will exaggerate the gap. So x is less than y. We want to keep it that way around. It should be e, I'm pretty sure. 10. Actually, it's e, yeah. You can go through and find counterexamples, like plug in the points of like 1, 2, or minus 1, 2, minus 1, 1. Do you mean to see which ones break it for? But this is the easiest way to see it. It's like, do you preserve the ordering? That's what it's asking. Do you preserve ordering? Well, if you square things, it gets rid of it. If you reciprocate things, it gets rid of it. But if you only do odd powers, that's what it's about. Odd powers, that preserves the order all the time. That's good. Number 11 then. It's a polynomial with real coefficients. It has 2 roots minus p and p, where p is positive. It doesn't really make a difference, does it? Consider the following 3 statements. So let's actually think, what does this mean? Like, we have some axis. We're going to have like the y-axis as well. Should be straight though, shouldn't it? And we have 1 point there, 1 point there. And we need to just go through those points and never touch this line again. So consider the following 3 statements. Which of them must be true? F dash is 0 for exactly 1 value between minus p and p. Well, no, I can draw one that breaks quite easily. I go through at p, or minus p, and I do a few wobbles, and I go back up. So I've got 1, 2, 3, 4, 5. So that's more than 1, isn't it? So goodbye, you're lying. Number 2 then. The area between the curving x-axis and the lines, the area under there, is given by this thing. Easy way to see it, this thing is equal to the integral there, not the area. So this is underneath the curve, yeah? It's going to be negative. Area, always positive. So, no, they're making stuff up. You can see it as well. This is only going to be true. Like, this one is true. If you ignore that negative idea, like the actual size of them, like the magnitude of them, that would be true if and only if it was an even function, i.e. all made up of completely even powers of x, or other even functions. Which you don't have in this case. You could have like x to the 4 plus x cubed, something like that, would still work. As long as you make this still happen, Jimmy. But there could be odd powers in there, would be fine. So the graph, we need to do some weird stuff to it, and it intersects at the same points. So what does this refer to? This one, we're reflecting in the x-axis. So the point here gets mapped to that one. The point here mapped to that one. And then this flips everything upside down. So 0 gets mapped to 0. So all that's going to happen effectively is, yeah, this one goes to there and this one goes to there. So they're still going through at P and minus P. So still completely fine. What this refers to, if you have two reflections that are perpendicular, so like we've done one on the X, one on the Y, it's the same as having a 180-degree rotation around the point of intersection of the lines of reflection. So we reflected through this line and this line. They intersected the origin. So we've done a 180-degree rotation around the origin. So our new function looks something like this, like doing the wobbles and come back down. So 3 is true. So it's 3 only, which is D. 11, is that D? Yes, it is. Number 12 then. The first term of an arithmetic sequence is A, common difference is D. Sum of the first n terms is Sn, yep, okay. If the 8th is bigger than 3 times the 6th, what can be deducted about the sine of A and D? Well, what will that tell us? So sine of 8, what we're going to have? We're going to have 8 over 2, yeah? Lot of 2A plus n minus 1, lots of D. Let's make that over 2, just a 4 at the front, yeah, a bit nicer. And for the 6 then, what we're going to have, so 6 over 2 will be 3 out the front. Similar thing inside, but 2a plus n minus 1, which is 5 lots of D. But we need to times that by a 3, because we had 3 of them. So it makes that 3 into a 9 out the front. And we want the 8 to be bigger than the 9. So let's expand these brackets. What do we have? I've got 8 A's. I've got another 28 D's. I've got 18 A's, and I've got 45 D's. So what I can do, I can have minus 10 A's is bigger than 17 D's. This then, we want to see like what signs can we make. Let's just plot this out. What does this tell us? If we kind of move this all to one side, we know that 10A plus 17D is less than 0. So if we were to draw that, we're going to have some line that's effectively just like, I don't know exactly what angle it'll be, but it's going to go through the origin like this. Depending on which one's A and D, let's pick which one which. Let's make U A and U D. So effectively, we want to have, yeah, A is equal to minus 17 on 10, lots of D. So let's actually swap that round to make our gradient look a bit nicer. So D and A. And we need to be less than 0. So let's think about which points can we put in. Like if I put in positive, positive, does it work? If I put in 1, 1, well, I get 27. That's not less than 0, no. So this quadrant is not allowed. Or this, not quadrant, but this region is not allowed. We have to be on this side. So we can have A be positive, D be negative, both be negative, or be down this zone where D is positive, A is negative. So do we learn anything specifically about any of the signs? No. There's lots of combinations that work. Just double check here, like both negative. Nope, we can be there. A positive, D negative. Nope, we can be there. Negative, negative. Again, negative, negative allowed. A is negative. Nope, can be down there. D is negative. Nope, can be other way around. Other way around. Neither can be deduced. So, lovely. 12, F. Are we good? 12 is F. Wonderful. 13 then, what's going on? Well, we have more positive integers. We want to prove the false statement. If A divides BC, then A divides B or A divides C. Just a quick note about notation. The symbol for divides, I'm going to write it looks like a given, that symbol. So it's going to be like A divides BC. And similarly, we will have A does not divide BC. I may well write that sometimes as A not, like A divides BC, but not. So this one for divides, one of these two for not divides. So what else do we need? Yeah, that's what it means. Yeah, it means it's a factor of as well. So for example, 4 divides 8. 4 divides 24. 4 does not divide 6. So it is a factor of, so I can read it. 4 is a factor of 8. 4 is a factor of 24. 4 is not a factor of 6. All good, yeah? Lovely. So what do they want? We want to prove a false statement. Which line contains the error in this proof? So let's read down then. The statement is equivalent to if A does not divide B and A does not divide C, then A does not divide BC. Okay, yeah, so let's actually think about our original statement. If A divides BC, so A divides BC, then, so that implies A divides B or A divides C. This statement down here, statement 1, is equivalent to, so this is something called a contrapositive. What that refers to is if we have like statement A implies statement B, then it's also true. So like if today is Monday, tomorrow is Tuesday. If tomorrow is not Tuesday, today is not Monday. So if it's not the answer to the thing, then you can't have come from the original thing. Does that make sense? So if today is Monday, tomorrow is Tuesday. If tomorrow is not Tuesday, today is not Monday. So let's use that and see if we can flip this around then. So we want to have not this statement anymore, but we want to have the not of the answer thing. There's proper words for answer and kind of starting bit, but don't worry too much about those. We want to have not this implies not the other thing. So A not B. A does not divide BC. How do we do this not stuff? Well, we've got like not outside a bracket. You can just expand the brackets to change everything. So it's going to be A does not divide B, intersection, like the union becomes the intersection, and then A not C implies A does not divide BC. Is that the phrase we ended up with? Same is equivalent to if A does not divide B and A does not divide C, then A does not divide BC. Lovely. Now then, suppose A does not divide B, A does not divide C, okay? Then the remainder when B, then dividing B by A is R, where that's true, yep. And the remainder when C by A is, yeah, okay, so that's good. So they're just like, that's how you can write down any number. Look at line 3, like B is equal to some amount of X's, some amount of A's, sorry, plus R, plus the remainder. C is equal to some amount of Y's, some amount of A's again, sorry, plus the remainder. So we can times them together. Does that look good? So we have AX plus R times by AY plus S. First one then is going to be A squared XY. And then I'll have AYR plus AXS plus RS. I wanted to take, yeah, A at the front. A lots of AXY plus YR plus XS. And there's no R, no A in the RS is there, so I'll leave that alone. That looks good. Is that the same? Yep. This looks good so far. So the remainder when dividing by BC, sorry, the dividing BC by A is RS. No. So this could be bigger than A. So what you have to think about, like this has two possibilities. Either RS is less than A or RS is greater than or equal to A. In this case, you're good. What they've said is correct, but we can only think about it in this path. Do you know what I mean? It's like this statement is only true if that is also true. So thinking about this path, then, like as long as the two numbers you have times together are bigger than the thing you're dividing, then it's not going to work. And this is quite a common thing. If you divide by 4 or something and you get answers of 3 and 2, you get 6, don't you? So it's possible. So that's the one that's not going to be true. 5 is not true. Is that correct? Yeah, looks good. 14 then. We've got some polynomial, some quartic. We've got 5 real numbers. F equals 1 has P solutions, 2 has Q, 3 has R, 4 has S. Okay, which of the following is not possible? Okay, so 1, 2, 3, 4. Let's draw some lines out. 4, 3, 2, and 1. So this is the value of Y on this side. 4, 3, 2, and 1. Let's move that up a little bit. And we want to have so many solutions at each of them. How many solutions are given by these bits? So we can think about having, which one's P? Sorry, P is the lowest one. P is for F equals 1. So we want to have, in this case, 1, 2, 4, and 3. So because the 1's at this end, this has to be like, it's going to be like a positive 1, yeah? Because otherwise we'd have to, there's no way you can have 1 for the last one, because how are you going to do that? How are you going to get both these bits up there? So we must be coming down to the 1. So how do we get to that 1? If we've started up here, end up there, we've gone to here and gone back there, we can't leave the page. We have to go through that line twice. That's all they wanted for that line. So we can no longer touch any of these again. We have to go up then. I think we want to find which ones are not possible. So if we can make this, it's not good. We don't want to be able to make it, basically. We want to get 4 for the next one. Well, you can see I need to get 2 from each of these, don't I? Let's move this over to the middle a little bit. So I'm going to have to go up like either side for each one, like that. I do want to come back and touch it again. I need to touch here. So let's think about the left-hand side I can just send away. So that's done. This right-hand side, I need to touch it twice at the top. So like say there and there. But I do need to touch this row 2 more times again. Let's say there and there. I'm just going to move these over a little bit. So what we can do then, we're going to come from there, down, down, up, 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 down. We need to actually go through there and then come back again, but not touch this line. And that seems fine. We've got 1, we've got 2, we've got 4, and we've got 3. So A is not the answer. So let's look at B then. We have 1, 3, 2, and 4 as the numbers. So the bottom again being 1, we need to make sure that we have a turning point down there. We will therefore have these two coming up. And we may as well just send the top one to the left. So that bit's all done. We can't touch down here again. We need to have another bit there. So there's kind of 2 options. Either we could turn straight away and come back up, or we go and like turn here, do we come back down, turn there, and go back up again. Both do kind of the same thing. Doesn't make a huge amount of difference. So yeah, going up, come back down, hit that bit, and go back up. We go straight through here then, and we need to still get another 1 or 2 up there. I'm sorry. So coming through, and then at least 2 more. So back down, back through again. So this works, but there's one big issue. We have 1, 2, 3, 4, 5 turning points. We're not allowed that. At most, we're allowed to have 3, 1 less in the power there. So this is not possible. You need to have a higher order polynomial to make it work. So B should be the answer. 14, is that correct? Yeah, correct question is B. You can go and double check all these to make sure that they do work, but as soon as you get one that doesn't work, it should be fine. 15 then. So 15 then, we have some quadratic. It has 2 real roots, whose difference is greater than 2, less than 4. So let's complete the square, find out what those roots are. We'll have x minus p, all squared. That would be minus then p squared, and plus a q. And setting this all equal to 0 then, and rearranging, what we end up with, well, we'll have p squared minus q, all square rooted, plus or minus that, and then adding on a p. So the difference, 2 times this thing, yeah? So doing that, what's going to happen? We'll have 2 lots of p squared minus q, all square rooted. We want it to be greater than 2 and less than 4. That looks good. Let's divide everything by 2. We'll have 1 less than p squared minus q, all square rooted is less than 2. And then squaring everything, 1 is less than p squared minus q, which is less than 4. Looking over here then, we do have 1 with p squared minus 4. Sorry, p squared minus q, that, isn't it? So none with p squared minus q. So let's add q to everything. Q plus 1 is less than p squared, which is less than q plus 4. That looks good. So let's rule some things out. Like we have p squared in the middle. So let's look at all of those first. P squared, p squared, p squared, p squared. Is it going to be q and q plus 4? So that side's correct, but this side's not. So no. Is it going to be this one? Well, if we take 4 from everything, this will be minus 3. This would be minus 4. This would be 0. That works. But wrong signs. So not working. We'll see here it's greater than 2 and less than 4. Cannot be 2, cannot be 4. That would be the same as including it. Next one then. Let's make it minus 1 in the middle. That would be minus 1. This would be plus 3. This would be 0. 0, minus 1, plus 3. That matches. Correct signs. All looks good to me. Again, you can go through and rule these other ones out, but this is the correct one. So that looks good. Yeah, let's keep going. 16 then. Got some trapezium. This is parallel to this. The diagonals, they meet at point X. U lies over here. T is over there. So it's that this is the same as that, or parallel to that. Let me get rid of that bit. Yeah, this is 12. This is 3. How long is this? Okay. So we have similar triangles. These lines are parallel, so we can draw a big Z and show that this and this are the same. We could draw another big Z, pop, 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 show that this and this are the same. And then we can use the X angles, like the angles at X, the vertically opposite ones, to show that they are also the same. So we have similar triangles, the top one there, bottom one there. This one is 12, this one is 3. So the bottom triangle is 4 times bigger than the top one. So that's going to be true for the height as well. And therefore it's true for like this section. If you think like if this is 1, this bit must be 4. So effectively, how long is this length? Well, it's going to be like this is going to extend up to this. It's going to stretch out from 3 to 12. It does that linear. It's a straight line, so it's going to be a 1D stretch doing linearly. So we start at 3. We're going to end up going to 12. So 12 minus 3, that's a change, is like 9. And we're 1/5 of the way through that change. So 1/5 of 9 is 1.8. Plus the 3 gives us 4.8, which is one of the answers. I think another way you could do it is think about like this being a similar triangle, like this being a triangle, and then this one being a similar triangle. So you can see that we need to have, there's 3, we need to have 80% of that 3. So this is 2.4. Mirror this, 2.4 that side as well. So it is going to be 4.8 together. Looks good. 17 then. We have simultaneous equations. Y is 3x plus 2, and y is x plus c. So which of the ones are true? Okay. So let's draw out that sine function first. We're going to go through, not from the origin, but if we think about having the kind of shape of it, going up, down, and down again. I'm going to keep drawing just a few of them, yeah. So that's good. We'll go left a little bit as well, get some more. And this has got a gradient of 3. So we can think about a few bits, like what values do we know when we look at this? So this point on the y-axis is going to be 0, 2. When we get to that kind of same part of the wave, do you mean like when we're the same height and we're also going up? That should be, again, having the height of 2. But now we've shifted across by 2 pi. Let's draw that a bit neater than it is. 2 pi. What I'm actually doing is just put the 2 pi down the bottom. Ooh. Go back to being big. Let's put the 2 pi there. That looks good. Get rid of this stuff, do the same thing, put that as a 2. Lovely. So we have some rough points. We want to see now, for some value of c, there's exactly one solution between 0 and pi. So again, we can mark on some point. This is going to be pi, isn't it? Yep, going to be pi. And there's exactly at least one solution between 0 and negative pi. Let's do a similar thing. This is negative pi, isn't it? Stretch you out. Negative pi. So what do we want? Exactly one solution between 0 and pi. So we need to hit this at some point. We know the gradient of it is going to be a bit shallower than this. So thinking like this is pi, that's more than 3. So how high is this? Well, this is at 5 in at the top of it because we had 3 sine x. So what we know, if we think about this point being pi and 5, if we were to draw the line, it is not as steep as that. No, sorry, it's steeper than that. It's steeper than that because this goes across pi and up 3. We need to go across 3 and up pi. So we'll hit it just to the left-hand side of that. So where was that point? It was here. We want to be not there, but a little bit steeper than that. Something along those lines. I will draw this longer so we can do a bit more stuff with it. Something like that. So this is good. So now it's basically, the c is the thing we vary, which is the intersection, the y-intersect. So it's the same as moving this, just up and down. You think about moving left and right as well, because it's still like, this point just changes, do you know what I mean? But yeah, just moving this up and down, what's going to happen? So exactly one solution between 0 and pi. We have that. There's at least one between minus pi and 0. Yep. So this one is possible. That's good. Second one is exactly one solution between 0 and pi. Yep. There are no solutions on the left. Can we do that? So is it possible basically to go there? It looks like it, doesn't it? Let's double check though. So if we make it go through at this point, are we allowed to be pi? Sorry, next one. We are allowed to be pi. So if we say that we want like x plus c, that's the curve that we have. And we also want it to go through the point pi 2. what do we get then? C is equal to 2 minus pi. This itself, if you think of what number that is, this is bigger than 3. So this is less than minus 1. So really where our intersect is actually is underneath the curve completely. We're already lower than minus 1, and that's the lowest this thing will ever go to. So this point really is actually underneath this. Do you mean should become like that? So definitely here we'd never hit that curve again because we should be entirely underneath it. So it's possible. That's true. Should we get all of these be true? I think I've got a feeling they shouldn't all be true. That didn't like the arbitrary. So similar thing down here then. Like one solution 0 to pi, and there are no solutions x is greater than pi. So it works. I mean, the same one works. We don't hit it again here. So that's good. Yeah, h 1, 2, and 3. Lovely jubbly. Next one then. So consider the statement about a function f of x. If the square of f is always less than 1, less than or equal to 1, for all between minus 1 and 1, then the integral of that square between minus 1 and 1 is less than the integral just from minus 1 to 1. Okay, not of the square of it. So does squaring it basically make the integral smaller, is what they're asking for. So if this is true, so which ones provide a counterexample? We need this to be true first before we consider anything. So if we can break that, we're happy, do you know what I mean? So let's have a look at the first one. If I can at any point, if I can plug in a number between minus 1 and 1, and I can make the square of this be bigger than 1, if I can ever make just the function be bigger than 1, because this is the same as having minus 1 is less than f is less than 1, or equal to. So we want to find basically some number between minus 1 and 1, and we plug it into these, we get a number outside minus 1 and 1. Here, fine, plug in 1. So f of 1 is bigger than 1. Here, plug in minus 1, and that's less than minus 1. Here, similar thing, f of 1 is bigger than 1. Here, I don't think we can break it so easily, looking at it from my head. Here again, f of 1 is bigger than 1. And again, can't just break it immediately. So those 4 that we've got there definitely cannot work, because they don't even satisfy the if part of it. Do you know what I mean? Like for all of this, like it's not true for every single one. So next bit then, let's think about actually what's going to happen in these. Well, this thing, it's just the integral. So what we're going to see for this one, this is an odd function, because again, we only have odd powers of x. So it's basically rotationally symmetrical around the origin. What that means is when you do an integral with minus 1 to 1, or minus anything to the same number, so minus b to b, the integral is always 0. The integral minus 1 to 1 of f of x is equal to 0. This thing needs to be less than or equal to that. It's the integral of a square. Squares are never positive. So this thing itself is bigger than or equal to 0. But this one equals to 0. And it must be less than this one. So this one has to be 0 as well. But that's only going to work if the function is completely 0 all the time. So not true, because we have that square. It means so it's always positive. It's always never negative. So it can never have, like, if you go above once, you need to take that away, and you can't do it. So how to write that down a bit nicer? Well, basically, we know that this one is not the case. It should then be f, because you see this is not going to work. Oh no, sorry, other way around. Like it breaks it. It breaks it. That's the correct answer. F should be not then. Double checking that then. So yeah, if we think about this, what we have is that f of x squared is bigger than 0, or basically it's not equal to 0 for all x's that we're considering. So for all x such that x is between the minus 1 and 1. So therefore, when we do the integral, it is bigger than 0. Just definitely. And this is 0, so this one is not smaller than this one. Let's double check that is correct. 18. Correct answer is D. Lovely. 19 then. Yeah, so this, okay. We have some identical unit cubes are used to construct a 3D object by gluing them together face to face. Sketches of the object are made by looking at it from the right-hand side, the front, and from above. They're called the side, front, and plan view of elevations. How many cubes were used? So what we have on the right-hand side there is some squares. I'm actually going to bring them over here, but easier to think about. And they represent the top, the middle, and the bottom layer. Imagine like a Rubik's Cube. So we've got 27 altogether, yeah? 9 in each row, with this being the top, the middle, and the bottom. So let's think about the plan view first of all. This is looking top down. These are all looking top down as well, so it's very easy to think about. We can see we don't have any in there. So those ones, we can just get rid of them all. I will cross most of these out to show we don't need them. But for this one, first of all, we can just actually just eliminate these. They're never going to be there. We're not allowed to have any of them. It gets a bit tricky. I'm actually going to undo that and just cross them out. It's a bit tricky, like knowing which one. Like, say we had one left, like which one is that? Do you know what I mean? Like, is it this square or this square, etc. So we will leave them and just cross all out that we don't want. So none of those are allowed. And then let's start looking at the other ones then. So let's do the front elevation. So the front, we're going to imagine we're looking from this side on all of them. So let's look at the top row first. We need to make sure that we have nothing on the left too. So we're not allowed to be there, but we do need to have something in that column. For the middle then, has to be nothing in the middle. So again, nothing there. But we need to make sure we do see something there. We didn't see these two, so we must see the one in front of it. So thinking this column is like hidden behind here. This column is hidden behind here. This column hidden behind here. So again, we don't know any more information about that, apart from the fact that we need to have at least one of them. Looking at the bottom then, have to have all three that we can see, so you can't really rule anything out there. Looking at the side then, let's do the top again. So this is that, so we can't see anything there. This is this, so we need to make sure we can see at least one of them. So this one has to be done because the other two were missing. And same idea, this one we're missing everything, so it has to be missing everything there. So top row we're done. We have one cube on the top. Middle then, looking from the side, we need to make sure that when we look down there, we see something. Well, we already do, so that's good. So no more information gained about that. From the middle, it's going to be these three, yeah. So we do need to see something. We don't see the two on the left, so we must see that one. And here, we need to miss everything, so we're not allowed to have that one. And then on the bottom, from the front, did I miss it? I think I missed a lot tonight. Did I do the front? Yeah, so the front elevation, we have to make sure that we see something like this is these ones. And this is going to be these ones. So these ones, do you mean down here? And then looking at the front, we need to make sure we see something there. From the side, we need to make sure we see something everywhere as well. So with the side ones, like this is looking down there. So we do see something. And this one is looking along there. So we do see something there as well. So we've got those two squares left. What happens with those? So let's think about, like, if we remove them, what breaks? Can we remove both of them first of all? Well, we need to make sure when we look from the plan that we do see one of them, because we need to have something in that corner. We don't have this one, so we must see one of these. The front elevation, again, we must make sure that we see something along, like the middle here is that one. We do see something like that, fine, so it doesn't affect us at all. And down here then, this is going to be the bottom along there, so we do see something already, so that's fine. Looking at the side then, this is going to be here, so it's the middle, looking that way, so it's this one, but you already see something. And down here then, again, we already see things when we look from that side. So we don't have much information, but we need at least one of them. Can have both, that's fine, but we need at least one. So how many do we definitely need? 1, 2, 3, 4, 5, 6. I thought it was actually more than that. Yeah, hold on. I should have more than that one. What one have I got slightly wrong? The bottom layer is okay. The middle layer. Actual answer. Bottom layer. We do need that one. Why do we need that one? Hold on. Plan view. Looking down, we had something. Side elevation. Oh yeah, sorry. Side elevation. We needed this bottom one, didn't we? So let's add that one back in. There, that looks more than what I was expecting. So we have, yeah, 1, 2, 3, 4, 5, 6, 7, definitely. And then one of these two. Could be both, but at least one of them. So 7 plus 1 or 2. 8 or 9. Looks good to me. Number 20 then. Each interior angle of a regular polygon with n sides is 3/4 of each interior angle of a second regular polygon with m sides. Okay, so in general then, how do you work out the total of the interior angles? Is 180 times by how many sides you have, take away 2. And I think for each angle then, we divide that by how many sides there are. So that's for the n. If we do it with the m, it's very similar. 180 m minus 2 over m. And each with n sides is 3/4 of the one with m. So 3/4, like that. And they should be equal to each other. Let's cross some things out. 180 and 180. Goodbye, goodbye. And we'll expand and rearrange everything. So 4m times n minus 2. So it's going to be 4mn minus 8m equals 3n times n minus 2. So 3mn minus 6. Lots of n. I've got nm, I've got nm. So I can make 1mn is equal to 8m minus 6. Minus 6n. This is looking okay. We want to make, like, how are these actually going to work? What are we going to do with them? We know that they must be integers. They have to be, because of the fact that, like, we're counting triangle, like we're counting how many sides there are on a polygon. There can't be like 2.5 sides of a shape. It must be exactly a whole number. So we know these are all going to be integers. Let's think about slightly rearranging things then. So let's divide by mn. We know 1 is equal to 8 over n minus 6 over n. So they're all going to be integers. What numbers are possible? Well, we need to make sure this equals to 1. This needs therefore be bigger than 1. We can't have less than 1 size, can we? Also, m's and n's. This should be an m. Yeah, this thing, m is always positive, yeah? 6 is always positive. So this thing is always positive. So we're taking away that. So we're taking away something positive. We're making it smaller. This must therefore started bigger than 1. So that tells us that n is less than or equal to 7. So what can we have? N can be 3, 4, 5, 6, and 7. So that's good. Let's rearrange for m then to make our life a little bit easier. So as we do that, there's the m. If we add that over, we'll have 6 over m is equal to 8 over n minus 1. Make this into one fraction on the right, 8 minus n over n. Flip everything over, m over 6 is n over 8 minus n. 8 minus n, and times by that 6. 6n over 8 minus n. And remember, this must be an integer. Integer. Has to be a natural number, really, doesn't it? So what does that tell us? Well, they need to work out nicely, don't they? So let's plug these numbers in. What are we going to get? For 3, we get 6 over 5. Nope. For 4, we get 24 over 4. That looks good for me. That's 6. That looks good. 5, we're going to get 30 over 3. That's 10. That's good. 6, 36 over 2, 18. That's good. And then 42 for the last one. So that's good as well. So how many altogether? 4 of them. 1, 2, 3, 4. Is that the correct answer? Number 20. Where is it? Where is it? E is the answer. Yes. Yeah, lovely, jubbly. So that was good. That's not too bad as they go, I don't think. Hopefully it all should be doable for you. So yeah, good luck. Hope that's all nice. Thank you very much for watching. I will see you later.